So, remember that first time, so long as I have been it's not so I'm willing to. And then we've spent 3 hours because it's all the bar stuff is like this. Yeah. But I mean, like, mine is the only one that works, so that's the one we're using.
Oh, okay.
Do you need to?
I do, yeah.
Okay.
Yeah. So I was going to have, I put Philip first and second.
Okay.
All right. And
So yeah, the question was, did you present from here or from there? So we said, well, like do it here.
you can do that, or I can move your slides for you because they probably want you to stand in a few.
No, they said
here is fine.
Okay, all right. That's fine.
We can move this mic over here so that it's fine.
Okay, I think this mic's probably working, right?
Even if you're standing? Like, yeah.
I think so, yeah. Yeah. Oh, yeah, we're late. All right. We have a Jabber scribe. I have a minute taker, but I also need thank you, Melinda, but need a Jabber scribe. Okay, thank you. Good. So I'll owe you a drink. All right. Is this going to work? Okay. Oh, that's not a very good color. What's that about?
Yeah, I have the same problem as well.
Ooh, is that readable enough?
Yeah, it's readable.
Okay. All right. Well, I think it's because I'm ombuds team, so I'm influencing it to be horribly green. But thank you.
For lunch. Seems like at least one.
What?
You didn't have to do it for lunch.
No. No. Ooh.
You had this cover in the previous meeting as well.
Okay. Huh. Okay. Well, I wanted to first of all say ahoy to everybody because I was very taken by the hello in Czech that we learned about last night. You are under the note well as a attendee of the research group, so do not feel that you can get away with reading all that boilerplate. And also, we follow the IETF's anti-harassment policies, which I put up on the board last night in the plenary if you were there. Okay, and the agenda today is I have a little bit of an update on the IRTF, and there's a longer one with more silly pictures that you can find in the minutes from Sunday. Sunday. And then our 2 Applied Networking Research Prize talks. And I should warn you that we have plaque presentations and photographs too, shaking hands kind of things. So tolerate us during that. And then if we have a little bit more time at the end, I want to get people to just say, I'm on a listening expedition. What do you need in terms of publications if you're working in the IRTF? So be thinking about that and come up to the mic and talk about that. Okay, so for those who don't know, I think you do, we have a parallel between the IRTF and the IETF. The IRTF was founded to kind of take on the longer term work and to not have some of the process strictures and time frame that IETF has. So it actually goes back to the beginnings of the IETF. It's not a new development by any means. And we're organized into a bunch of research groups. This is not a research group. This is the area meeting. And then also there's a steering group with the research group chairs, and some at-large members. Because if you were at the plenary, you heard me say this last night too, it's very unusual that everybody meets at the IETF, but this time everybody did. So I think everyone must like Prague, because they don't have to meet at IETF. They can meet in different ways. So this is the list of the groups we have. And we also had a proposed research group, the Path-Aware Networking Research Group, PAN-RG, which is, our RGs are formed in a different way from working groups. They convince the chairs with some consultation, and then we give them a year to take off or not take off. So they're not exactly chartered, but they're in a proposed state now. And then we also had some initial organizing for a group that's currently called DIN, that would be about blockchain and crypto ledgers and things like that. It needs to organize its thoughts. Okay, and Saturday we had the annual Applied Networking Research Workshop. There's where the proceedings are, and you could also see the recording if you weren't there. So one thing that's confusing is we have the ANRP and the ANRW. And so the ANRW is kind of a standard research workshop emphasizing applied networking, so the intersection of IETF style things that we do and research. And so that's going to happen again next summer. Take a look at it. Let us know if you're interested in submitting to it. And then we have the ANRP, which I'll tell you about in a few moments. So this is the IRSG membership, and it also shows you who are the chairs of the research groups. So you can just run your eyes over that. And then my cats don't look very good in green and purple, but I find it calming to see them. And so we have a discuss mailing list and an announce mailing list that you can join. And IRTF.org has links to extensive information on the research groups, but you can also find the research groups through the data tracker. Okay, so we're going to move on to the Applied Networking Research Prize talk, starting with Philip. But I also wanted to mention that this prize is a submission of papers that were already published. So it's kind of like a best paper, but pan-internet best paper award. So we ask for people to submit what they think of as the best papers they've seen anywhere, and to nominate a speaker who would benefit from experiencing the IETF and the IRTF. So the winners of this receive a trip to the IETF and some hospitality from ISOC involving attending the IETF Fellows dinner, I believe. And you should, even though we're meeting this late, you should think about ways that you might encourage these speakers to participate in IETF when you hear what they've talked about. So with that, I'm going to introduce Philip, who is just about to defend dissertation. Is that right? Yeah. And then move to a position with Dave Clark at MIT, and has a a great study of a multi-perspective analysis of carrier-grade NAT deployment. So over to you. And here is your dongle. And I'll move over.
Thanks. All right. Can you guys hear me all right? Also with the mic like this? Okay, sounds good. Okay, yeah. My name is Philipp Richter. I'm going to talk about our work, multi-perspective analysis of carrier-grade NAT deployment. No, I think we agreed on presenting us from here. With the,
Don't we have remote participation?
yes.
There used to be camera there and things like that.
So-
They can adjust the camera. So
They told us here is fine.
the info.
Camera.
Yeah, okay. I think the cameras are all pointing to me. Okay. Yeah, so I'm going to present our work on carrier-grade NAT deployment in the internet. This is a paper that appeared in last year's IMC conference. And if you're interested in the PDF, you can also get it using this tiny URL link here. I also want to acknowledge my co-authors here. So this is joint work with Florian, Naseo, Mark, Randy, Anya, Christian, Nick, and Vern. Okay, I think there is no need for a long introduction of what the problem here is. I guess everybody in the room is aware of the problem of IPv4 address space exhaustion. In fact, it receives a lot of attention, more recently also in the media, and it is also a long-standing problem. So I just found this quote here a couple of days ago from IAB, from an IAB meeting in 1992, and already back then the problem of too few IPv4 addresses was clearly named as a clear and present danger to the future successful growth of the worldwide internet. Now that was in 1992. If you now fast forward to 2017, now we have a situation in which 4 out of 5 of the regional internet registries that manage global IP address allocations exhausted their address pools, and currently we have only about 1% of the globally routable IPv4 address space that is still unallocated and usable. And of course the question is, what do networks now do to mitigate their IPv4 shortage issues? And the first thing that comes to mind, of course, is the transition to IPv6, which will present a long-term solution to the scarcity problem. And in turn, it also receives a lot of attention from the measurement community. So when it comes to IPv6, we have plenty of measurements and statistics available. I will just show you 2 very common ones. You might have seen them a couple of times already in the last days. The first one is from Google. And it basically tells us that as of today, about 20% of the hosts contacting Google can do so using IPv6. The second one is from a PNIC Labs that measures IPv6 adoption on a per country level. And here we can see that we are doing quite well in some countries, but still also there's a lot of red color in this map. Now, besides transitioning to IPv6, ISPs can also use other means to mitigate address shortage issues, and in particular, they have 2 other ways of doing that. Now, the first one is to buy IPv4 address on address markets. And the RIRs, like the registries, recently introduced policies that allow these transfers and also publish statistics regarding these transfers. So also here we have data available that we can look at to track how these markets are evolving. What I show you here is just some data pulled from the RIRs that shows some statistics of the number of address blocks that are currently or were bought and sold and on address markets in the recent years. And here we can see that this is indeed, the markets are indeed taking off. But then there's a third thing that network operators of some networks can do, and that is that they can use IPv4 carrier-grade NAT to multiplex more users behind fewer public IPv4 addresses. And when we started looking at carrier-grade NAT, we soon realized that there are no deployment statistics available, so it's really hard to keep track of how popular this way of combating before exhaustion really is. And also very little is known about how carrier-grade NATs are configured in the wild. And this is the focus of this work and also of this talk. All right, now first we wanted to get a bit of an understanding of the problems that ISPs face when deploying carrier-grade NAT. So we performed a little survey So we asked ISPs about their IPv4 scarcity issues and whether they want to deploy IPv4 carrier grade NAT. So we circulated this, and eventually we received some 75 answers. Just want to quickly show you some of the highlights of that. So probably the most important question that we asked is like, did you or do you plan to deploy v4 carrier grade NAT? And we were quite surprised. I mean, of course, 75 ISPs is a small sample, but we were quite surprised that 38% of the ISPs told us, yes, we already do that. And another 12% told us that they are in early trials and they will deploy v4 carrier grade NAT in the near future. So we went on and asked them also a little bit more about carrier grade NAT specifics. So we asked them what if they have any operational concerns when introducing v4 carrier grade NAT, and there were plenty. So one of the most commonly mentioned one was that subscribers might experience problems with applications that just don't work well behind carrier grade NAT. So gaming was mentioned several times. Another issue that came up frequently is the traceability of users behind carrier grade NAT, and also issues with publicly facing gateway IP addresses becoming blacklisted. Now, we also asked them what they see as the major challenges or caveats when introducing carrier grade NAT. Troubleshooting connectivity issues was frequently mentioned, but also more generally, how to dimension carrier grade NATs, meaning how to do the resource allocation, like how many IP addresses, how do I allocate IP addresses and ports to subscribers, and how do I set the right quotas for individual subscribers. One thing that several ISPs mentioned, and I want to mention that here because we will also see some effect of that in our measurements, is that their problem with v4 carrier grade NAT is a shortage of internal address space. And it means basically that they have used the available RFC1918 ranges already in their management network, and now they have problems finding address ranges that they can use behind their carrier grade NAT. Okay, we also gave them a free text field where they can tell us more about what they think about carrier grade NAT, and what we can clearly see is that most of them were not really fond of deploying v4 carrier grade NAT, as you can see also from the first comment. But a surprisingly large number of networks also told us that v6 deployment seems to be costly and difficult for them, so some of them just opt to first go with carrier grade NAT. So basically that really motivated us to study this more, because it seems to be widely deployed, and the networks also voice concerns like regarding carrier grade NAT deployment. At the same time, we don't have broad and systematic studies available. So what we did is we developed methods to detect carrier grade NAT presence in the internet, and also methods that allow us to extract some of the properties of commonly deployed CGNet instances. Before I talk about our methods, just want to quickly introduce some terminology. So here in this figure, you see a common case of how a subscriber is connected to the internet. So we have the ISP in the center. The ISP has some public IPv4 address space, peers with other networks in the internet towards the right, and hands out a public IPv4 address to its subscribers. In turn, the subscriber will run a home NAT and will connect his or her devices behind that NAT. So that would be the canonical case. Here we don't have CGNet deployment. Now, if this ISP now decides to deploy carrier grade NAT, we will have an additional NAT box that sits within the ISP, and then the ISP will hand out internal address space to its subscribers. And that gives us two more cases. Like the first one is the case of NAT44, carrier side NAT, which basically means that here we only have one NAT box, but the NAT box sits within the ISP and not at the end user. And then we have the third case where the ISP deploys a NAT box, hands out internal IP addresses to the subscribers. In turn, the subscriber runs another CPE NAT. So here we have the situation of NAT444. Okay, I mean, this is what carrier grade NAT deployment looks like on the whiteboard. Of course, like in practice, there are more complicated scenarios possible. So our goal was to find ways to detect the presence of these devices. This turned out to be really difficult because NATs operate transparently, right? Meaning that if you monitor traffic, if you monitor packets, there's no easy way to tell whether this packet was translated at some point on the path before we can see it. So we had a hard time with that, but eventually we found two methods that allow us to detect carrier grade NAT presence, and I will now introduce them to you. The first one, the first method that we found to be working is what we call detecting CGNet from the outside using BitTorrent. We call this one from the outside because with this method, we don't need any probing devices within the networks that we want to test, but we can, this detection works by crawling the BitTorrent DHT. Let me quickly walk you through. I guess everybody here knows the BitTorrent protocol, and in the classic way, BitTorrent would work the way that you want to download a specific torrent, you will connect to a tracker, tell the tracker I want to download torrent XYZ, in turn the tracker will give you a list of IP addresses and port numbers of other peers, you connect to them, you download your content. But you can also do that without using a centralized tracker. You can do that using the BitTorrent distributed hash table. And if you do that using the BitTorrent DHT, then each BitTorrent peer that participates in this DHT will maintain a list of IP addresses and port numbers of other BitTorrent peers that it recently interacted with. And actually, it turns out that we can use these BitTorrent peers in the BitTorrent DHT as vantage points in our study. So in order to do that, we implemented a DHT crawler, which is basically a machine that continuously asks BitTorrent peers across the internet, BitTorrent peers participating in this DHT, and we ask him, hey, please give us a list of IP addresses and port numbers of other peers that you recently interacted with. And in turn, they will tell us, okay, I can reach peer, each peer has a unique ID, I can reach peer XYZ using IP address and port number. Now we had this crawler, we implemented this crawler, and we had this crawler running. By the way, initially not for the purpose of detecting NAT, but it turned out that we can do it partially with that. So we had this crawler running, and after a while we realized that in some instances we have BitTorrent peers like this peer here that apparently sit behind some form of a NAT and tell us that they have connectivity to another peer using an internal IP address. So for example, shown in this case, we ask a specific peer, the peer tells us I can reach peer 8A2D using an internal address. So they leak us internal IP addresses via the BitTorrent DHT. Now, when we realized that this is happening, we tailored a crawler to extract and harvest as many of these internal endpoints from the BitTorrent DHT, and we can do that quite efficiently. So within 1 week of crawling, we can learn private IP addresses from more than 700,000 peers in 5,000 ASs. Now the question is, do all these 5,000 ASs necessarily deploy carrier-grade NAT? And the answer is, of course, not, right? Because at this point, we just know that there's some form of NAT, but it could be a carrier-grade NAT, or it could just be a home NAT with multiple BitTorrent clients behind it. Okay, so to better understand this, and also to be able to dissect these small home NATs from carrier-grade NATs, you have to have a closer look at the leakage relationships. And what we basically do, what we basically do is that we form a graph. And whenever we have a peer, BitTorrent peer A, that leaks us the contact information for a peer B, like this one, and peer B has a private IP address, we will form two vertices in the graph, where the leaking peer, peer A, is a big blue vertex, and the internal peer, the peer with the internal IP address, is a small red vertex. And then we draw this arrow to show, okay, peer A leaked as peer B. And then we have a look at these leaking relationships at a larger scale. So namely, we form a graph for each AS in which we crawl BitTorrent peers. Now let me show you what these graphs look like. So this is a tiny subset of our data, of course. I mean, we crawl many more of these peers, and it shows us two ASs. And in the first AS, we did not detect carrier-grade NAT, meaning that here we do see leakage. We see BitTorrent peers leaking us internal IP addresses, but typically they only leak us 1 or 2. And also, and that is more importantly, all of these leakage relationships are isolated. So in this case, we cannot say that they are an indication of a carrier-grade NAT, but it could just be home NATs. But then we have other ASs like the ones on the right-hand side, where we see much more leakage. And the important thing is here is that we also see overlaps in this peer leakage, meaning that we have different BitTorrent peers using different public IP addresses, leaking as the same internal peers, which is indicative of a NAT that has ranges of public IP addresses, which we use as trigger for carrier-grade NAT detection. All right, of course, I mean, there's much more thresholding involved, and we have to post-process these graphs. We have more details on that in the paper. But here I just wanted to give an impression of what this signal looks like for NAT in BitTorrent. All right, so with this method, we can test some roughly 2,700 ASs in which we crawl a sufficient number of BitTorrent peers, and we detected carrier-grade NAT, meaning these clusters form in more than 250. Now the benefits are clear that we have a broad coverage and that we can just do that and we don't need to put any probing devices within these networks. The problem is that first we need a lot of BitTorrent activity in ASs so that we can even, that they can at least in theory show up in our measurements. And secondly is, even if we have significant BitTorrent activity in a specific AS that deploys carrier-grade net, it will not necessarily show up here, because the net must be configured in a very open way. Namely, it must expose internal IP addresses of BitTorrent peers to each other. So with this, we will only partially capture the carrier-grade net landscape. So we complemented that with a second approach, which is what we termed detecting CGNet from the inside using Netalyzer. We call this approach from the inside because here we have full control over probing devices that are located behind the carrier-grade net. So I want to quickly introduce Netalyzer. Maybe some of you folks know that. Netalyzer is a network troubleshooting suite. It is developed by IXI in Berkeley. And you can download it as an Android app or as a Java applet, or you can use it as a command line tool. And when you download Netalyzer and execute it, it will run a series of tests regarding the health of your connectivity, and it will also show you a detailed report showing you lots of properties of your internet connection. At the same time, when you run Netalyzer, you will support our research because we use that in measurement studies. And in this particular study, we use data captured in more than 550,000 sessions. Like in a session just means a person executed Netalyzer, and they cover more than 1,500 ASs. And the benefits of this Netalyzer data is that it gives us direct access to the IP address of the client, of the router, and also the public IP address. And it runs in cellular and non-cellular networks. And since we have full control over Netalyzer, we also implemented more customized tests. Now we'll talk more about them in a second. Just a quick sketch on how we detect carrier-grade net presence with Netalyzer. Now here we have two different cases. We have the cellular network case. In the cellular case, detection is straightforward because in a cellular network, the IP address of the device will directly be assigned by the ISP. So we can compare the device IP address against the IP address that we see at our measurement server and say, okay, there was translation. Now in residential networks, the situation is a little more complicated because here the device IP address will always be assigned from the home router. So what we do here is that we use UPnP to query the external IP address from the home router. And again, we compare it with the server-side IP that we see. It turns out that in practice, this is much more cumbersome because in up to 7% of the sessions, we see cases that people have at least two home routers in cascade in their homes, meaning that the external IP address from the first CPE router is not assigned from the ISP, but from some other CPE device. And we developed several filters and heuristics to get rid of these sessions. If you're interested in that, that we documented that in our paper. Okay, that was a quick overview of detection using Netalyzer. In total, we tested some 1,500 ASs, and we detected another roughly 200 carrier-grade net instances and also 205 cellular ASs using carrier-grade net. Now, the benefits here are clear. We have much more control over this measurement point, and it gives us direct access to the IP addressing data that we need to detect carrier-grade net. The problem here is, again, partial visibility. This is crowdsourced data, and we are at the mercy of users executing this for us. Okay, now let me show you some carrier-grade net deployment statistics. Now, first, when talking about like what percentage of networks deploys carrier-grade net, of course we need to define into what kind of networks we are interested in. And so in this work, we want to focus on eyeball networks, meaning ASs that primarily connect end users to the internet. So the first thing that we did is that we defined our set of eyeball AS and a population of ASs that we consider eyeball ASs. And we do that using two different data sources. The first is the Spamhaus PBL list. This is basically a list where you can register residential address ranges. And the second one is a data set from APNIC Labs, which gives you an estimation of the number of subscribers in a particular AS. So we use these two to define our set of eyeball ASs, which is about 3,000 ASs. And when we have a look at how many of them like we cover with our measurements, we see that we cover roughly 62% of them. And in addition, this is for the non-cellular case, and in addition, we tested in total 218 cellular ASs. Okay, now how many of them do deploy carrier-grade net? Or let me rephrase, in how many of them do we detect it? For the non-cellular case, we end up with a little more than 17%. And maybe if you now recall our survey, in the survey it was 35%, we measure 17%, so the real number might be somewhere in between. And what is probably interesting to note here is that if we partition the ASs that we tested according to the 5 different regions, we can see that carrier-grade net deployment is particularly pronounced in the APNIC, in the Asia-Pacific region, and in the RIPE region. And it's important to point out here that these are also the 2 regions where addresses ran out first. Okay, now for the cellular cases, we see that carrier-grade net is just everywhere. So more than 94% of the networks that we tested do deploy it. There are only some very few exceptions in Africa where you still have a chance of getting a public IPv4 address on a cellular network. Okay, so much for the deployment. Now I want to talk a little bit about some of the properties of the nets that we identified. Now the first thing I wanted to show you is the internal address ranges that networks use behind their carrier-grade net deployment. Now, both our methods allow us to study that, and we show that here, again, for the non-cellular and for the cellular case. And what we can see is that the RFC 1918 ranges, particularly 10/8, is still the most commonly used one, and the relatively newly allocated 100.64, which is specifically allocated for the purpose of deploying carrier-grade net, only slowly takes off. But what is probably more intriguing to see here is that up to 20% of the ASs already use multiple internal address ranges behind their carrier-grade net. Now, if we recall also from our survey that it seems to be an increasing problem for ASs to find usable internal address ranges to use behind the net. Now, this goes as far as that in the case of some major cellular networks, they seem to see the need to use routable IP addresses as internal IP addresses behind their carrier-grade net. And in this figure here, I show you some of the most prominent cases. I want to say here, we don't want to do any name shaming. We see this behavior for more ASs. We just chose to show these 6 because they are like really big, so we have a lot of data and can be confident in our reasoning here. So what we show here on the x-axis is the corresponding routable address block, and here we show the networks that use them as internal space. And what we want to highlight here is that, like, for example, let's have a look at the 25/8 address block. If I recall correctly, it is UK Ministry of Defense. And currently, if you go from the global routing table, this address block is not in use. But what we see is that there are at least 4 major networks that use these addresses internally. And there might even be more. As I said, this is just a subset of them. And we would argue that the question is, what happens if somebody wants to finally use this address block? Given that scarcity will increase, we can imagine that at some point people want to buy and use this address block, and we can likely expect that a lot of users behind these users of these networks will have severe connectivity issues here. Okay, now that was one of our findings. We implemented more customized tests in our Netalyzer test suite to extract more properties of the carrier-grade nets, and I would want to quickly sketch our methodology here. So one thing that we do is that whenever you run Netalyzer, Netalyzer will initiate 10 subsequent TCP connections from the device to our measurement server, and what we can then do is that we compare local IP addresses and port numbers to remote IP addresses and port numbers, and with that we can study how carrier-grade nets allocate ports and IP addresses. And for some of them, and I will show you an example, we can also estimate like how many ports an individual subscriber receives. We also implemented a custom TTL-based net test. And basically what this test does is that it sends TTL-limited probes to first create state in all nets on the path, and then to retain it in some hops, but to expire it in other hops. And with this test, we can pinpoint the location of nets on the path, including carrier-grade nets, and also extract timeout values of the nets. And lastly, we also implemented a stun test, which allows us to compare the kind of net mappings that a carrier-grade net would give you in contrast to your home router. Okay, there's probably not enough time to go into all of these results. I just picked some of them that I quickly want to show you. One thing that we found quite surprising is that up to 20% of the carrier-grade NAT instances that we detected use what's called arbitrary pooling. What it basically means, these are NATs that have ranges of public IPv4 addresses. And if they use arbitrary pooling, it means that you as a user, if you initiate 2 subsequent connections, your public IP address might very well change. This is something, of course, discouraged in several RFCs, and we were surprised that we see it to that large extent, because just think of what this does to, for example, host reputation systems. We also studied in detail the port allocation behavior. Just want to show you a quick sketch here. So NATs have different strategies on how they allocate ports to its subscribers, and we were interested in studying whether there's some sort of a common uniform behavior even within a specific AS. And it turns out that this is not the case. So up to 70% of the ASs in which we detected carrier-grade NAT have a mixed port allocation strategy, meaning what happens to subscriber A will not be the same as what happens to subscriber B. We have more details on that, of course, written up, but generally, when studying resource allocation, we see a huge diversity here, and we also see that actually the majority of them shows non-uniform behavior. And of course, just think of what this can do to applications, to host reputation systems, or also to attribution. I want to quickly show you one case, one port allocation strategy, which we really like because it is very measurement friendly. Some carrier-grade NATs do allocate ports in a chunk-based fashion, meaning that every subscriber receives a specific chunk of ports, and then it will randomly choose port numbers from this chunk. And in our measurements, this then nicely shows up, because for each Netalyzer session, we can see, okay, the chunk size in this particular ISP is 512 ports, or is 1,000 ports. And this in turn allows us then to reason how many subscribers are behind a single IP address. And the most intense case that we found here in our measurements is 512 ports per subscriber, 128 subscribers per IP. Now, I heard more crazy numbers. People told me that they NAT thousands of users behind an IP. I don't know. This is the highest number that we can somehow empirically back up here. Okay, I want to quickly show you one other thing, because I think it matters. We also implemented the stun test, and as mentioned, what the stun test does is that it measures somehow how restrictive or how open the mapping types are that a NAT uses. And first, I will not go into detail of all these different mapping types, but let's first quickly look at the distribution of filtering and mapping and filtering behavior for home NATs. And the only thing I want to point out here is that the most restrictive way of configuring a NAT is using symmetric NAT bindings. And it basically means that if you are behind such a NAT, you can't do any peer-to-peer anymore. And even if you use advanced hole punching techniques, it won't really work. So meaning if you are behind a symmetric NAT, that's it basically. And in the case of CPE devices, we see that this is quite uncommon. So only about 2% of them do that. But if we look at our carrier-grade NATs, we see that these very restrictive NAT bindings are much more common. In fact, it's about 10% of the non-cellular deployments, and even 40% of the cellular deployments show this behavior, meaning that the mapping that a carrier-grade NAT imposes on its subscribers is often more restrictive than what your CPE home device would do. Okay, so that was a quick overview of some of the results. What we can generally say, I mean, we see that carrier-grade NAT is very broadly deployed, and it is a everyday reality for a lot of users. I think, in fact, it is even reality for the majority of internet users, considering that most of them are in cellular networks. And what we see in this first study, we see a stunning variety of different configurations. We see that when we compare networks to each other, but we also see that even within networks. And what we also see is that the degree of resource sharing, meaning how many ports, for example, does an individual subscriber receive, varies vastly across different NATs. Meaning that we can clearly see with these measurements that carrier-grade nets just limit the resources that are available to subscribers, and also it means very different things for different ISPs. Now that raises some challenges. So for example, one regarding measurement, and I'd be very curious also to hear your opinion on that. So for example, when we do measurements to measure end user performance or internet performance, I mean, the common metrics would be speed, latency, and packet loss. And the thing with these with these metrics are that they don't necessarily capture the limitations that a carrier-grade net imposes on you. So for example, to capture them, we would need metrics like, for example, what is the maximum number of concurrent connections that I can issue as a subscriber of a particular ISP? Or what kind of net mappings will that ISP impose on me that restrict my connectivity? And yeah, related to that, we also wanted to point out that perhaps given how widespread carrier-grade nets are deployed and given their measurable effect on how much internet you receive as a subscriber, whether there's a need for more guidelines or possibly like best practices on what is still considered an okay amount of internet, or whether that is also something that could be interesting or subject to regulation. All right, with that I conclude, and I'm happy to take your questions.
Jelinkova, one comment and one question. When you're saying about 20% of ISS doing arbitrary mapping, it might be just different devices. You have one CGN device and one location, another CGN device next to it,
yes,
which has different pools, and you just randomly hit one or other.
Yes, yes.
And question, did you compare your data with detecting V6 only networks, which do not 6.4, because it looks like you were connecting to V4 destinations?
Yes, so actually most of that is currently V4 only, most of these measurements. The thing is that the BitTorrent, the public DHT of BitTorrent is very sparsely populated in IPv6, so currently we can't really compare it there. And for Netalizer, we do have V6 data available, but we didn't include it yet here in this.
Yes, thank you, because it would be very interesting to say the 94% of mobile ISS doing CGN. It would be interesting to see what they're doing in terms of NAT64.
Yes, just one quick thing, because I expected, of course, questions regarding IPv6. I just did something which is not a great analysis at this point, but just did it yesterday. So I took the ASs in which we detect carrier-grade net, and I just checked whether they at least announce an IPv6 prefix. And here we see it's about half of them.
Hi, Alan Johan. First, a follow-up on this, and then another question. There are two cases. You can have service provider would do IPv6 and IPv4 carrier-grade NAT, and some can do simply IPv6 native internally and NAT64. Those are two different cases that you may want to somehow separate. The second question is about the routable addresses that you found, and for me that was the most surprising finding in your study here, and very, very interesting, because you're right. Once those blocks are going to be on the market and chopped off in smaller blocks, then we may see some interesting behavior. So do you publish a list of actual addresses that you have seen something at a finer granularity than the /8? Because I look in your paper, you only go to the /8.
Yes.
But publishing this data to maybe a /24 granularity would certainly help a lot.
Okay. Okay. Yeah. I mean, we didn't do that yet, but if there's interest in more fine granular data, I think we can do that.
Thank you.
Hi, Anshul from Boston University. So you looked at the different deployments by different ISPs. How many of these are compliant to the standards? How close are they? What are their strategies?
You mean to RFC?
Yeah, whatever standards are. Yeah, RFC probably.
So, I mean, there are lots of RFCs on net behavior, and some also on carrier-grade nets. The thing is, they don't specify all these, to my best knowledge, they don't specify all the things that we measured here, but they do specify, for example, that arbitrary pooling of IP addresses is not an option. So at least 20% will violate that. And in other measurements, which I didn't present you, but we also measure timeout values, and we find that pretty much, I don't have the exact number, but that a large number of the carrier grade NAT boxes also violate them. So there's a large fraction of them that are for sure not RFC compliant.
So there are specifications in RFCs, but these are the people who are not compliant with it.
Yes, there are specifications in the RFCs regarding NAT mappings and NAT timeouts. But for example, what is not specified in current RFCs is how many ports, for example, you need, or how many sessions are appropriate.
So it's both problem.
Yes.
Okay.
Eric Nordmark, thank you. This is a very interesting study. So I saw one thing, you had two things. You had this sort of port behaviors, whether it was, preserving or what, I forget the term, but, and you also had the restrictiveness, whether it's symmetric or something else. Did you actually look at potential correlation between those two? Meaning that there's sort of, if you group them together, that things fall in different buckets?
No, that's an interesting thing to do. We didn't do that yet.
Okay.
Hi, I'm channeling Wolfgang Beck. When STAN was introduced, it was discovered that some NAT devices changed their behavior when running out of ports or addresses. So a full cone may become symmetric. Did you observe this with carrier grade NATs?
No, I mean, I saw that too, and I found that also really impressive that this can happen. I don't see a way of how to measure that, because in the end, like for one session, we can execute these 10 TCP connections and we can run the stun test once, and it's not that the same user will be nice enough to run Netalyzer the whole day, but that would certainly be something very interesting to study.
Alison Menke, I have a question, but also if there's any more, we can take a few more minutes for this. So this is one of the nice things, is having a chance to discuss. My question was, with this kind of behavior that you observed, why do you think that, how can reputation systems work at all? Is there any way that you could study the kind of impact of this on people's, persistent use of addresses for reputation?
Yeah, honestly, I don't really know how reputation systems should deal with that, or how they currently deal with that. I would be very interested in speaking with somebody who runs such systems.
And there might be people who have some hacks. Okay.
Well, maybe Dave.
Matt Ford, thanks. This was a really interesting talk. I had a question and a comment. The question was, did you go back to any of your survey respondees once you had the measurement results to establish whether there were false positives turning up in your data set?
Yes. I mean, generally, validation is very difficult because no ISP writes that on their website, or at least very, very few do. We had a limited set of like a couple of dozen of ASs for which we have like ground truth on whether they deployed or not. We did not find false positives so far. We have several false negatives. I mean, we try to adjust our thresholds to be as conservative as possible. And so far, we didn't find a false positive, but that might happen at some point sooner or later.
Thanks. And the comment was just, I think you made a comment on one of your last slides about regulation, and I thought I just observed that I was just looking. I know there's some regulation in Belgium related to this now, and I was looking for that, and the first thing I found was a press release from Europol with lots of text in it about how alarmed they are at the growing use of CGN and the impact it's going to have on their law enforcement capabilities, and they cite your paper in that press release. So I thought that was awesome. And I've also heard of subscribers of ISPs using CGN having problems getting to major, Pokemon Go was another thing that came up high up in my search results, and Xbox. There's all kinds of breakage this is causing for subscribers. So it occurs to me that given the impending regulation, or it seems likely regulation, and the effect this is having on subscribers, continuing to measure this over time, you might start to see this stuff goes away as well.
Thanks, Philip. You and I have talked about some of this stuff before, so I'll echo one of the questions that I have for you, but I don't expect you to be able to answer it. But I'm fascinated by Philip's work in that there are clearly a whole bunch of kinds of commercial devices out there that do these things, and no one says, hey, that's the JBox one, that's the CBox one, that's the Linux one. Somebody must know. So if somebody in this community could tell us about what they are, that would be fascinating to know. They also have a cost and capacity, presumably, and I don't understand why this marketplace isn't described in the open. Why don't I just have a 4-color glossy that says this is the thing that does this? The question that was asked before about reputation and across, for instance, the World Wide Web client space, not speaking for my employer because I'm just not authoritative about what exactly we do in our reputation product, but I can tell you some of the things that you can do. There are pieces of software that have unique identifiers in them, and you very often see tens or hundreds or even thousands of those unique identifiers show up behind one IP address in a day or a couple of days. So clearly that's an added address. The other thing, one of the most interesting ones that we're pursuing in our nascent research is about finding v4, v6 address pairings, sort of the way that AppNIC does, where you force a web browser to connect back with both protocol versions. And over a very short amount of time, you'll see 1/24 associated with tens or hundreds of thousands of /64s in v6. So it's an interesting way in that the temporarily unique identifiers in terms of the identities assigned in v6 multiplex onto v4 addresses, and you can find the nets that way. And then the last thing, following up to what Allison's, she said, like, I think the gist of it was, how in the world would you do this? It's a huge problem, and it's a huge record-keeping problem because you have to continually monitor this. And the other place we're seeing it is people natting through cloud infrastructure. Yeah. So like the cloud, right? They have a NAT that's infinitely scalable, and people are putting commercial enterprises behind a cloud. And so we see a cloud address one day and it's one machine doing some service, but the next day it's a company behind it with 1,000 employees. So really difficult problem, and I'm glad that's not my job.
All right. Okay. Anybody else? Thank you for the great talk.
Thank you.
I'll introduce you here. Steve Checkaway is a professor at the University of Illinois, Chicago. And this is a really interesting talk for the security folks and all of us. Good thing to pay attention to. So thanks. And again, we can take extra time at the end. So think of good questions to ask him.
Okay, great, thanks. So as Allison said, my name is Steve Checkaway. I'm at the University of Illinois at Chicago. And I want to talk today about the incident involving Juniper's use of dual EC. So if you don't have any idea what I'm talking about, I'll jump right in. So in late 2015, Juniper made a pretty surprising announcement. They had an out-of-cycle security bulletin that said that some unauthorized parties had gained access to their source code and had managed to introduce 2 backdoors. So the first was an unauthorized remote administrative access, and the second was this somewhat cryptic message that a knowledgeable attacker who can monitor VPN traffic can decrypt that traffic. So this is what I want to talk about. This work is all about how did this actually happen? What was it that the attackers were able to do? What the consequences of that are, and then I want to end with a couple of lessons that I think that we've learned from this that are applicable to protocol designers. So first, these are the devices that were affected. These are the Juniper Secure Service Gateway combination firewall and VPN devices. And the affected versions of the software were a variety of ScreenOS 6.2 and 6.3 versions. So let me start with the first one. This was actually, from my point of view, the least interesting one, although it was a little bit clever here. So basically what the attacker did was they introduced a hard-coded backdoor password that affects Telnet and SSH. And so this is the password right there. And you can see that it kind of looks like, if you can read this, it kind of looks like some other format strings that you would be using for logging information. And it turns out that you can see this is being passed right here to stir compare. And so if you log in with this password, it lets you log in with administrator access, and it leaves some telltale sign in the log, which one could actually remove. So this was found really quickly by H.D. Moore, and was able to test it, and sure enough, it worked. So the next one was more interesting from my point of view because it was really cryptic. It just said there's this knowledgeable attacker who could do something. And so once this security bulletin was put out, researchers around the world, including me and my colleagues, decided we were not going to spend Christmas with our families, and instead we were going to spend a bunch of time reverse engineering stuff. And the question is, well, where do we start with this? Well, H.D. Moore, again, was very, very helpful here. He ran strings over one of the versions of the firmware that had been known to have been changed, and also ran strings over Juniper's fix that they put out, and ran diff over that. And this is almost entirely the full diff. There's a few other things, but this is the key point here. And so this is kind of interesting. If you are a big crypto nerd, you might have looked at this and said, oh, I know what these are immediately. If you're like, most people, you put them into Google and see what comes up. And the first 5 of these long hex digits, long hex numbers here, are parameters to NIST's elliptic curve P256. So these, you Google them and they come right up. And so the question is, what does this change here? What changed from 9585, et cetera, to 25 or 2C55, et cetera? And to figure that out, we had to reverse engineer the binaries. And it turns out that these 2 values, or rather this one value that was changed, were for the x coordinate of a non-standard elliptic curve point, which was used for Dooley C DRBG. And if you haven't heard of Dooley C DRBG, it is a pseudo-random number generator that was designed by the NSA in the early 2000s. And then they made a push towards standardization. So it appeared as part of an ANSI standard. I think it appeared in some other standards. Eventually, NIST standardized it in special publication 800-90. Just as sort of a footnote here, the NSA paid RSA $10 million to make Dooley C their default random number generator. It doesn't actually do anything else in this for this particular work, but it's an interesting thing to note here. But the key point, sorry, I couldn't resist. The key point here is that in 2007, some Microsoft researchers, Shumo and Ferguson, were able to demonstrate at a crypto rump session a theoretical backdoor attack against Dooley C. And sort of after this, people thought, well, okay, we know this is bad. It has some biases that we probably shouldn't use it. And it turns out it's really slow. No one would ever use it. So let's ignore it. In 2013, there was some renewed interest into this when a New York Times article was written as a result of the Snowden revelations that revealed that the NSA was trying to tamper with some particular crypto primitives, and that Dooley C was perhaps one of these. And then the following year, some of my colleagues and I showed that, in fact, that if you use Dooley C as your random number generator for TLS, then you can actually break TLS. So fast forward to 2015, and we see that once again we can actually do this with Ike. So let me talk about what it means to have a backdoored random number generator, because that's kind of an unusual concept. But basically, the way a normal random number generator works is you start with a seed. So you have some seed value, S0, to which you apply a pair of functions. So you apply f of, or you compute f of s naught, and you get s1, which is your new state. You compute g of s naught, and you get some output r1. And then you can just repeat this as many times as you need, subject to some theoretical or, I guess, practical constraints on how many times you can do this. But you can do this to keep getting more output. Now, where the back door comes in is if someone who has some sort of secret knowledge is able to start with, say, some output R2 and apply some other function to it using this secret knowledge and recover one of the internal states of the generator. And the reason that this is really bad in a crypto protocol is probably pretty obvious. Once the attacker gets the internal state of your random number generator, well, then they get every subsequent random, pseudo-random number that will be generated until the PRNG is reseeded. Now, dual EC, the EC stands for elliptic curve. And so just you can do a quick primer on elliptic curve math. You don't need to understand most of how this works, although it is a pretty neat area. So basically, a point on an elliptic curve is a pair of x and y coordinates that satisfy a particular equation. Doesn't matter what the equation is here. For our purposes, x and y are going to be 32-byte integers, although there are larger and smaller elliptic curves that one could deal with. And sort of the key properties here are that you can add 2 points on the curve in this sort of geometric fashion and arrive at another point on the curve. And you can repeat this process over and over. So you can take an integer n and a point p, and you can compute n times p, which is just adding p to itself n times. And finally, the key to this whole scheme is that given a point p and a point np, it's hard to come up with n. So this is the elliptic curve discrete logarithm problem. So let me describe dual EC here. So this is sort of a somewhat simplified version of how this works. But we start with a 32-byte state, S naught. And we take S naught, we treat it as a big integer. We multiply it by some fixed elliptic curve point P, which is the generator for P256. And then we take the x coordinate of that, and that gives us a new state S1. We take S1, we multiply that by a second fixed elliptic curve point Q, take the x coordinate, and that gives us R1, which is not quite our output, it's almost our output. So what we do is we take the least significant 30 bytes of R1, and those become the most significant 30 bytes of our output. And then this process repeats. So take S1 times P, take the x coordinate, that gives us S2. Multiply that by Q, take the x coordinate, that gives us R2. The next 30 bytes, or the least significant 30 bytes of that, are the next output bytes, and so on. So the really cool thing that Shumo and Ferguson noted about this is that if an attacker knows the relationship between P and Q, in particular, if the attacker knows the integer D such that P is equal to D times Q, and it turns out that such a D exists, and the attacker is able to see output from dual EC, then it's actually possible to recover some internal state. And so the way this works is pretty neat. You start with the output and you set R1, which you don't know, except you know the first 30 bytes of it, just because of how dual EC works. Then you need to guess the 2 most significant bytes of R1, or in reality, what you do is you just try all 65,000 possibilities, so that doesn't take very long. And you find an elliptic curve point R that has R1 as its x coordinate. This either succeeds and you find 2 points, or it fails and you find 0 points, in which case you would just try the next most significant byte. And now you take R, you multiply it by D, and you take the x coordinate, and if you... Oh, indeed. No worries. So you take the x coordinate, and that gives you S2. And If it was not immediately obvious how that works, you can read this string of equations here, or you can just take my word for it. But most of the time, you're not going to get a value that works. So how do you figure out when you've actually recovered the internal state? Well, it's pretty simple. You just walk dual EC forward. So you multiply your assumed S2 by Q, take the X coordinate, and then you check, is the least significant 30 bytes of R2 equal to the remainder of your output? And if it's not, just go back to step 2 and pick a new value for R and try again. And otherwise, you have recovered the internal state of the generator. And so what is it that an attacker needs in order to do this? Well, obviously, the attacker needs to have the secret value D, but the attacker also needs to see a large amount of output from a single block of dual EC output. So say at least 28 bytes. And the fewer bytes you have, the attack becomes exponentially more difficult. So if you have 30 bytes or more, it's basically free to do. If you have less than 28 bytes, you actually have to spend a lot of time working on it. And next, you don't actually need to see raw output to do the comparison step. It's sufficient if there is some public function of that. So let me give you an example. Imagine a network protocol that has a 28 or larger byte nonce that gets sent in the clear, and it has a Diffie-Hellman public key that also gets sent in the clear. So here we don't know what the private key for the Diffie-Hellman public key is, but that's okay. We can use the Shumo-Ferguson attack on the nonce to recover some proposed internal state of the generator. Then you compute what X would be just by following however X would be normally generated in this protocol. And then you compute G to the X and see, did that match the proposed, did that match the actual public key or not? And if it did, then you know you've got X and you have basically broken the protocol. So you might wonder, how can one learn D? And I've got 4 methods that one could use to learn D here. The first is you could solve the discrete logarithm problem. The second is you could be the entity in charge of picking the official Q value in dual EC. And so either way you do this is you just pick a large integer E, you multiply E times P, you set that to be Q, and then D is just the inverse of E modulo the group order. So some simple math, and you've got D. Third, you can use a non-standard point Q. You don't have to use the NSA's Q value, and just do the same thing as in step 2. Or you can gain access to somebody else's source code and substitute your own Q point just as you would have done in step 2. And it's worth pointing out here that solving the discrete logarithm problem is too hard. We just can't do that. Picking the official point was done by the NSA, but they're not saying how they picked it, so who knows. Screen OS that was used in these Juniper boxes actually use a non-standard point Q. And finally, this incident that I'm talking about came about because the attackers replaced the Juniper's Q with their own Q. And so now we can sort of answer the question, what was it that the knowledgeable attacker knew? Well, the attacker knew the discrete log D. So this was actually pretty surprising because there's a 2013 knowledge base article that says that although some of these Screen OS versions use dual EC, it doesn't matter because dual EC is not the primary PRNG. And in fact, it takes the output of dual EC, feeds that through an ANSI PRNG X9.31, and that's what gets used as the main output. And so in light of this, we had, my colleagues and I had 5 research questions that we really wanted to answer. So why doesn't the use of X9.31 defend against some compromised Q value? Why does a change in Q actually result in VPN decryption? Because this is just a random number generator. Perhaps other things should be able to defend against this. What is the history of the Screen OS PRNG code? Where did dual EC come in, and how did that lead to being able to decrypt traffic? And then, are there versions of Screen OS that are using Juniper's Q that are vulnerable to the same passive decryption? And finally, how did Juniper actually generate their Q value? And so we were able to answer a subset of these questions, the first three, by drawing on a body of firmware revisions. So in this table on the right here, this is the list of revisions of the firmware that I reverse engineered to some greater or lesser extent in order to answer these particular questions. So we can answer the first three questions, but unfortunately, if we want to figure out the answer to the last two, we're going to need some other body of material that we just don't have access to. Although, presumably, Juniper knows the answer to 5, which, as we'll see, will answer 4. So let's start with ScreenOS 6.2's pseudo-random number generator. And let's start by looking at the PRNG function over here on the right. And so keep in mind, this was decompiled code. So any of the names that you see here are names that I came up with, not names that appeared in the firmware. They're probably very different in Juniper's actual source code. And so this function has a couple of key features here. The first thing is you'll notice that there is a conditional reseed. So it seems pretty standard. Some condition is met. The reseed happens. Second, we can see that it's always generating 32 bytes of output at a time using the ANSI X9.31 PRNG. If we look over on the left, we can see the reseed function, and the key points here are that we're using dually C DRBG to generate 32 bytes of pseudo-random values. The first 8 bytes of this become the new X9.31 seed, and the remaining 24 bytes, the remaining 24 bytes become the X9.31 key. So at first glance, this looks like exactly what Juniper described. We have dually C here, but its output is being fed into X9.31, so there shouldn't be any problems with this particular use. But let's take a closer look here, because it turns out that's not true. So the first thing that happens over in this PRNG function, or PRNG generate function here, is that we're setting this index global variable here to 0. Then we call this one-stage RNG function, which it turns out always returns false, which means that reseeding happens every single time this generator is called. So then if we look over at the reseed function, it's generating 32 bytes from dually C. The index global variable is set to 32 for some reason. And then back in the main generate function, this loop never executes because index is 32, so the loop guard is always false. And thus, at the end of the function, what we have is 32 bytes from dually C left in the output array, this global output array, which is the output of this particular function. So what's going on here? Well, we've got these global output and index variables, and they're being reused for different purposes. So the output variable is being used both as a temporary 32-byte buffer for the reseed function, and it's also being used as the main output for the PRNG. And this index variable is global for some reason that doesn't make any sense. And we'll actually come back to this later when we look at the history of this, like, why is this global? And I should note that a bunch of people were looking at this code and were saying, well, I don't understand how anything could go wrong with this, including me, until Willem Pinkers on Twitter pointed out that that when the reseed happens, the ANSI generator is in fact not being run. So he was the one who figured out the key to this whole thing. And so from this, we can answer our first research question. Why doesn't the use of X9.31 defend against a compromised queue? Well, X9.31 is never used, so it can't possibly do anything. So to answer the second question, which is why does a change in queue lead to passive decryption, we, somewhat unfortunately, need to talk about the internet key exchange. So IKE is used, among other things, for establishing traffic keys for VPN sessions. And there are two major versions of IKE, which I'll call IKE v1 and IKE v2. And both of them have two phases, which is, at least seemed to me, coming from a TLS world, somewhat unusual. But the first phase establishes keys to encrypt the second phase, and the second phase establishes keys for use for IPsec or some other sort of encapsulated protocol. And in both cases, these are basically classic Diffie-Hellman protocols. So let's, if we take a look at one of the IKE phase 1 packets that gets transferred, we can see that there's a header and a series of payloads that follow it. So there's a payload that says which crypto algorithms are we going to use. There's a key exchange payload which contains a Diffie-Hellman public key, G to the X. And there's a nonce which the standard says should be between 8 and 128 bytes long. And in ScreenOS, the private key is this 20-byte value X, which is generated by dual EC, and the nonce is always a 32-byte value, which is also generated by dual EC. Now, in an ideal world, an ideal for the attacker world, I should say, the way the attacker would attack this is by applying the Shumo-Ferguson attack basically directly. So if the nonce is generated before the private key, then it looks something like this. So we have to run dual EC a few times, we get a nonce, and we get this value X. And so what you do is you run the Shumo-Ferguson attack on the nonce, which gives you this internal state S2, and then you just generate X, compute G to the X, and you check, did that work? So it's basically what I described before. Unfortunately, what appears to happen, if you look at the code and you look at the protocol, is that the nonce appears to be generated after the Diffie-Hellman private key is generated. And so the Shumo-Ferguson attack doesn't actually recover X, right? So you run your attack over here on R2, you get S3, but you've missed out on X because X has already been generated. And you can't try to run your attack on X because if you had X, then there wouldn't be anything to do. So that doesn't work. So initially, I was a little disheartened when I saw this because it seemed like you would have to deal with multiple connections, but it turns out that the reality is somewhere between the ideal case and the apparent case. ScreenOS contains queues of pre-generated nonce and Diffie-Hellman values, and the reason it does this, presumably, is to speed up VPN connections. These boxes are not super powerful, and computing G to the X could be an expensive operation. And so critically, the nonce queue is always filled before any of the other queues. So there's a timer that fires, and once a second, it will say, I'm going to generate one value, and either I'll generate a nonce or I'll generate a Diffie-Hellman public key. And it always does the nonces first. And the consequence of that is that in many cases, the ideal attack really just works. The nonce was generated before the private key. And so you look at a transcript of a single VPN connection, and what do you see? Well, you've got the nonce and you've got G to the X, and you can run the attack on the nonce and get X. And I guess I should point out that it is in fact possible for the nonces to be generated after X. For example, if you make a bunch of connections quickly, you can exhaust the nonce queue before it's had a chance to refill. And then in that case, you have to deal with multi-connection attacks. And you can see the paper for all the hairy details about that. One interesting thing about IKE is that, at least for IKE v1, the authentication mode that is chosen, and for IKE v1 at least there are 4 authentication modes, actually has an impact on the traffic keys, on the encryption keys, not merely on the authentication. And so if you have authentication via digital signatures, then the attack works exactly as described. There's nothing more that you have to do. If you're using IKE v1 with pre-shared keys, then it turns out that the pre-shared key is actually mixed into the traffic keys. So the attacker needs to know the pre-shared key in order for this attack to work. And for the 2 modes involving public key encryption, well, the nonces are encrypted and there's just no way to run the attack, and it doesn't work at all. And interestingly, in IKE v2, the authentication modes don't affect the traffic keys at all. So the attack just works. And that's that's kind of sad. We would like later versions of a protocol to be more secure against attack than earlier ones. But in this case, that's not true. So what about phase 2? Well, phase 2, some more nonces are exchanged. Optionally, another Diffie-Hellman exchange happens. And to attack this, it's actually pretty easy. You can either just rerun the Shumo-Ferguson attack, or even easier is you could run the dual EC generator forward to just get the new values you care about. In the proof of concept that I'm about to describe here, we actually just ran the Shumo-Ferguson attack again because it was fast enough, and it meant we didn't have to bother dealing with values that were sort of generated far apart. So to test that this actually works, we bought a NetScreen SSG 550M, which you can see over on the right, and we replaced the Q value in the firmware exactly as the attackers did with a Q that I generated. So I knew the discrete log D, and then we set it up to have VPN connections with a variety of different configurations. And sure enough, the attacks worked as described. IKV1 with pre-shared keys, required the pre-shared keys. Using an RSA cert, it just worked fine. And for IKV2, the attack just worked fine. So that gives us the answer to our second research question. Why does a change in Q result in passive VPN decryption? Well, the dual EC output is right there on the wire. We just run the Shumo-Ferguson attack, and at least for some VPN configurations, that's sufficient. All right, so we figured out what the attacker did, and we figured out why it works, but now we have this question of why does ScreenOS do this? Is this something that was there from the beginning? Probably not. And in fact, one of the things that I did was I reverse engineered a whole bunch of other versions of the firmware that you saw on the table. And we can see that there are a number of differences between ScreenOS 6.1 and 6.2. In particular, 6.2 added dual EC in this cascade with ANSI X9.31. It moved from reseeding on every 10,000 calls to the generator to reseeding on every call. There was this bug with the index variable that was now global, so that it exposed the dual EC output. Even more interesting, the IKE nonces changed from 20 bytes to 32 bytes, and 6.2 added a nonce pre-generation queue. And so this set of changes actually raises a number of questions. Why were these changes made? So I want to go through them quickly and sort of offer my thoughts on them from an engineering, a cryptographic, or a standardization point of view. So why was dual EC added? I don't know. This was kind of a weird thing. I can't think of any engineering reason that would require this. And in fact, in 6.2, as far as I remember, the only thing that the elliptic curve math was doing dual EC. So they had to add a bunch of custom code to their OpenSSL version in order to use dual EC. So it seems like a weird trade-off to me. And I can't think of any standardization reason for doing this. ScreenOS was FIPS certified for X9.31 already, so they didn't need that. And in fact, they never got it certified for dual EC, so I'm not really sure. Next, why does ScreenOS 6.2 reseed on every call? So on the left, you can see 6.1, and on the right, we have 6.2 here. And you'll notice that this reseed counter, this global reseed counter, was retained in 6.2, but it doesn't do anything. It gets incremented, and then when X9.31 reseed gets called, it gets set back to 0. So the reseed value doesn't do anything anymore. So why does this happen? Well, I can't really think of an engineering reason to reseed every time. Maybe there's a cryptographic reason. Maybe they were trying to add backtracking resistance to X9.31. I don't know. Maybe a cryptographer could enlighten me. Could just be a bug. Next, there's the reseed bug. So in 6.1, we can see that output was initially a parameter to the PRNG generate function, and index was a local variable. Then, when they move to 6.2, both of these become global variables for some reason. I don't know why. I can't think of any good engineering reason for doing this. I can think of kind of a bad one, but it's not worth talking about. It could just be another bug, but it's a really strange one. I don't think I've ever changed a local variable to a global variable accidentally. So I don't know what's going on there. Next, we have the IC nonce size increase. So 6.2, as I mentioned, increased the nonce size from 20 bytes to 32 bytes. Again, I can't think of an engineering reason to require this. I can't think of a good cryptographic reason, although I will note that the Department of Defense had some bizarre to me line about how you wanted the public randomness to be at least so big, and so they wanted to do this in TLS. Maybe this was the reason here, I'm not sure. But I will note that at 20 bytes, the Shumo-Ferguson attack would take about 2 to the 96 scalar multiplications, which is completely infeasible. You would never be able to do it. At 32 bytes, it takes 2 to the 16. And finally, there was this nonce pregeneration queue that was added to the Diffie-Hellman pregeneration queues. So in 6.1, there was the Diffie-Hellman pregeneration queue by itself. And this is actually reasonable. As I mentioned, these are not very powerful devices. So perhaps computing g to the x mod p was sufficiently slow that they decided to do it ahead of time. That makes sense to me. In 6.2, they added the nonce pregeneration queue. And the only thing that I can think of here is that when I measured this on my laptop, dual EC was about 125 times slower than using X9.31. And so I suspect that what they did was they switched to dual EC and they tested how long it took to establish a VPN session, and it took a measurable amount of time. And so they said, well, here's where it's slow. Let's just generate this in advance. So I don't know that adding a nonce generation queue to handle the fact that your PRNG is slow is the right move to make, but it at least makes sense from an engineering point of view. And so if we look at these changes, we can see that the first 4 of them were actually required for VPN, for passive VPN decryption. If you didn't have these, then the attack just doesn't work at all. And the last change enables single connection attacks, whereas if you didn't have that, you would have to do this multi-connection attack. All right, so that's the history of the VPN, and that sort of leaves us with the final 2 questions. Are there versions of ScreenOS that are vulnerable? Well, maybe. It depends on how Q was generated. If Q was generated in a safe way, and I can describe one way of doing that, then no, the answer is it's not vulnerable. If Q is generated such that somebody knows this integer D, well, then yes, it's vulnerable to whoever knows D. And so that leaves us with the final question of how was Juniper's Q generated? And I just can't say. I don't know, and it's impossible to tell with the data that we have. And so I want to end with a couple of lessons for protocol designers that I think we've learned from this. So first, and this is sort of banal, PRNG is extremely important for cryptographic protocols. And so you should pay a lot of attention to what's going on with your PRNG. So one thing you can consider doing is hashing the output of it before you put it on the wire. If you have a good PRNG, this is a pointless step. If you have a bad one, maybe this will help you. I don't know. It would have in this case. Perhaps more important is you should look very closely at any proposed changes to the amount of PRNG output that is being put on the wire. We've seen instances in the past where the NSA has tried to increase the amount of random bits that go on the wire in TLS, and they didn't really explain why, and we should be very careful about allowing that. One idea is to use separate PRNG instances for your public random values and your private random values, and if all you need from your public ones is that they don't repeat, then this seems to work pretty well. If you need them to be unpredictable, then maybe this doesn't help you so much. And next is we should think carefully about the nonces that we're using in our protocols. For example, we should not allow nonces that are too large or that are variable length. Anything that's too large, for example, IKE's allowing up to 256 bytes, is unreasonable. It's just too long. You don't need that. And it just invites implementations to expose secrets, either intentionally or unintentionally by using bad random number generators. And it's worth pointing out that variable length implementations allow you to fingerprint implementations. So perhaps don't allow that. One thing that was really interesting to me from comparing Ike v1 and Ike v2 was, as I mentioned, that Ike v2 was less secure against a bad random number generator. And so maybe we should consider, whenever we have some low entropy, even low entropy secrets, we should consider hashing them into our traffic and authentication keys. And finally, I just want to end with talking about this concept of no-bus. So the NSA has this notion of nobody but us. So these are things that they don't feel like, these are vulnerabilities, for example, that they don't feel like they have to reveal because nobody but us would be able to exploit them. And dual EC is indistinguishable from a building block of a no-bus exceptional access mechanism. And I think that this is a pretty clear warning of what happens when we include exceptional access mechanisms either in our protocols or in our implementations. They can be co-opted by third parties, and that's just really bad. And so I think we should be very clear here in the IETF or IRTF that we should really not be building exceptional access into our protocols. Okay, thank you.
Plenty of time for questions.
Hi, Steve. Kenny Patterson. Let me just start by saying I think this is really amazing work, and you probably didn't tell us exactly how many hours you spent in the lab ruining your Christmas to do all the reverse engineering, and congratulations, it's really amazing.
Thank you.
I also have a question. What public statements did Juniper make about the penetration of their software development entity or section that led to this?
Right. So what public statements did they make? I think they had the out-of-cycle advisory that started all of this work, and then they eventually decided to remove dual EC from their products altogether. I think they made an announcement about that. I'm not sure if there's been any other public statements.
Okay. So they didn't make any public statements about the mechanism by which they were penetrated or the remediations they took in response to that or anything of that type?
Nothing that I've seen. I've been contacted by a number of reporters who have asked me if I had any insight into how that happened, and the answer is no. I have no idea how that happened.
Okay, thank you.
Thank you.
Hi, Stephen Farrell. Yeah, I totally agree with your last bullet.
I thought you might.
And I think this is a fine lesson, a demonstration of the detail of exactly the crap consequences if we did go so stupid. I hope everybody is listening and not just me and other people. One question, I think it's on your previous slide. You kind of recommend, yes, before putting on the wire. So there's the people who are interested in the Quick protocol are probably not here because I think they're meeting now, but they're having like fun debates about in a new transfer protocol what to leave in the public header that might be visible on the wire versus what to put in ciphertext, including things like packet numbers, which may not be sequential and may hence be outputs of randomness. So I guess it's a thought or a question if you've thought about if there are other kind of places in protocols that we might be exposing randomness, in ways we haven't really thought about the possible attacks like this.
That's a good question. I'm actually not sure all of the places that one might be exposing randomness. I mean, the obvious ones are nonces that we send, but I hadn't thought about sequence numbers. I guess I haven't looked at Quick in quite a while, but I would have assumed a sequence number was sequential, but you're saying that's not true, so I don't know.
So I haven't been involved in the details of Quick, but there was one mail earlier today on the list suggesting that you could randomly pick high order bits and then just have the low order bits sequential, which may give some better properties in some way, but I guess we need to think about being careful about that kind of thing.
Yeah, absolutely.
Phil Hambeck. Yeah, I'm just amazed that anybody would want to do this in the first place, because if you go back to your original slide when you're doing the dual, it's not like they're using the curve 25519 curve or whatever, where it's pretty close to the power of 2. I mean, these are the NIST curves and so on, and so they're going to. Is it even an unbiased random number generator?
No, absolutely not. It is biased, and one of the reasons that it only uses 30 bytes of the 32-byte output is precisely to deal with that. There's some analysis in SP 800-90 about why that was the right trade-off to use, and I admit I didn't totally follow why that was the case, but there is a bias. I tried measuring it, and there's some numbers in the paper about distributions of values you get, and it was pretty hard to distinguish. So the bias seemed fairly low to me.
Yeah, but I mean, like, you're going 125 times slower, and if you just fiddle around with Merkle-Damgard constructions, you can create yourself one that's unbiased for free.
Sure, yeah. I don't know why anybody would use dual EC. In that NIST special publication, there are 3 other pseudo-random number generators, one of which was designed by the NSA, the other 2 by, I think, John Kelsey at NIST, or others at NIST. And all of those are much, much faster than dual EC. There's no reason to use it.
Anybody else? Okay. Well, thank you to our ANRP awardees, and I'll come up again for a moment.
Thank you.
Thank you. I guess, I should have asked, I'm going to ask the queue. So are there any folks who are in the MeetEcho queue who wanted to ask questions to either of our speakers? Now, since I can't see it, you guys will have to tell me if anyone moves to the... Okay. All righty then. It's really hot in here, so I think that I'm going to spare you. I'm going to have a really long discussion now to use up every last bit of our time. Now I'm going to spare you further discussion, but I will ask, request some interaction on the IRTF discuss mailing list about some of the directions. I'll publish out the overview that I gave to the EDU team and ask you guys to give your views. And so thank you very much for being at this IRTF Open. Maybe you can go get some drinks early on and deal with your dehydration. And thank you so much to our speakers. You guys need to stay so we can photograph you getting your plaques. Sorry? Oh, yes. And if anyone wants to stay and applaud the receiving of the plaques, you're welcome to stay. All right. Till next time. We have 2 more awardees for the next IETF, so hold your breath till I announce those. These are both very good. Okay.
So what do we do now?
Well, we have to talk about who's going to tell us what's going on. What do you want to say?
Do you want to get the 3 of you together and then do you individually?
Okay. Okay, so I'll leave the plaques here for a moment. I'll bring the plaques. Okay. You want me to give them to? No, okay. I hope you also got to meet them. I saw enough people and get to have some good discussions. In particular, someone made a good suggestion that we should give you each a sponsor who, you know, who actually takes some responsibility for producing you around. And also have some, but the
You can know, yeah, the mechanics almost know IETF studies.
Yeah, okay, good, good. And if you haven't, you know, I'd love to see you back in our research group for those teachers.
Yeah, it's an initiative SCMS
Definitely.
The only reason they have c'est juste à côté. Peut-être à côté. Yeah. Il y avait un. Yeah, I didn't want to poke too much. He is one of the authors of this paper. I think you can move back.
Really been interesting. Actually, both of you have had really curious problems. So are you working on the work now as well?
I'm not at the moment.